or can even do. Computational considerations, we have the matrix is symmetric, the covariance matrix, of course. So we have this number n times n minus 1 divided by 2, covariance estimates, and then we have a quadratic programming problem. By the way, the same program is also running on the vector machine. There we had a universe of stock which is 110 stocks, which is a little bit more realistic. So a portfolio of between 100 to 500 stocks is a realistic portfolio, say, for mutual funds. So this will be their universe of stocks. For the sake of the RT, out of mercy, I reduced the number of stocks to 30. Otherwise it will take too long to wait. But of course on the vector machine, 110 stocks is virtually nothing. It's a very fast optimization. It takes about 5 seconds to find the optimal portfolio on the vectorized version. On the RT, it takes about 24 seconds to find it for 30 stocks only. So it was quite important to reduce the number of stocks that we use. What do we get out of this optimization? Each time we run the optimization program, we get 1 point on this curve, which is called the efficient frontier. And what we plot here is the risk, or the standard deviation, and the expected return, which are the two trade-off points. This is something which is known for any investor. I mean, obviously, risk-return trade-off is something that we all know about. The question is to find the optimal risk-return trade-off, because every point on this plane represents a risk-return trade-off. But consider point A, for example. There is a risk-return trade-off if you move away from point A, but if you move from A to B, you only gain, because B will have the same expected return as point A, but lower risk, lower standard deviation. And likewise, if you move away from point A to point C, you can only gain, since point C will have the same risk level as point A, but obviously a higher expected return. So what we would like to do is to find this whole line of points, which is called the efficient frontier. This is a collection of points which give us the best in this, in the way that I've defined previously, the best risk-return trade-off that we can achieve. So now I'll show you the plot that we get when we run this quadratic optimizer, and we get the efficient frontier. That, by the way, means that we have to run the quadratic optimizer for many, many points. You can extrapolate because it's a fairly smooth curve. And by the way, if without transaction cost, there is a complete analytic solution. You can prove that the expected return is a function not of the risk, but the variance is just a parabola. So it's a quadratic function. I have to apologize for turning my back to you, and hopefully everything will be okay here so I can show the program. I'll quit Speakeasy to make sure that I have enough space when I reload. I'm retrieving all the data that I saved before, the data that will have the points on the efficient frontier described above. Okay, now I'll try to graph it. The data is already stored in the namespace, which is a temporary storage area of Speakeasy, and the command is just graph EF, graph efficient frontier. And I get an error. Error terminates execution. The reason for it, now I can see what happened, I simply forgot to define the window. There's no window for the graph to appear, so I have to activate it by graphics X windows. Okay, now I have the window. I'm still in the program. It just halted in on this statement, so all I have to do now is to type resume, and it will resume the execution, and it will appear on the screen. Okay, this is the efficient frontier of this 30 stock, including transaction cost in this case. I don't know if you can see it, but there's a short red line right at the bottom, and I can just